Okay. A different architecture is so-called buck boost converter, and what we have in this case is the possibility of obtaining at the output a negative DC voltage, so a voltage which has an opposite sign with respect to the input voltage. So the circuit in this case is very similar to the previous one. Of course, as you can see, we always use in these DC-DC converters the same type of elements, because we want elements that do not dissipate power. And therefore we have inductances, capacitors, diodes, and switches. So this is the load. And this is Vin. Again, you can see what happens when the switch is on. The current can go in this direction. So we are energizing the inductor. We are putting energy in the inductor because, of course, you see the current, the voltage applied to the inductor is equal to the input voltage, and therefore the current in the inductor increases linearly with time. Okay? The diode is off, so VL is equal to V in. The current in the inductor goes up with the derivative that is equal to V in over L, and the diode is off, and this is of course because you see the cathode is at the highest voltage which we have in the circuit, so the diode must be off. When the diode is off, the load is only connected to the capacitor. So what we have is that the capacitor discharges itself on the load, so provides the current to the load. During the off period, when the switch is off, we have a different thing. Of course, the input is disconnected, and what we have is that the energy that was accumulated in the inductor pushes the current in this direction and therefore recharges the capacitor and has current through the diode. I must say that I made an error here. This current during T on is in the other direction, is in this direction. Okay. So, because you can see that basically during T off, the inductor continues to have the current through the in this direction again, and this current does two things. On the one hand, it recharges the capacitor, and on the other hand, it passes through the load. Therefore, in this situation, you have when the diode is on, the diode goes on because the current passes in the proper direction. The diode is on. If we neglect the voltage drop on the diode, then VL is equal to the output voltage. VL is equal to VO, and dIL over dt is therefore equal to VO over L. Okay, again we have the same, we have a situation which is very similar to what we have discussed before. Of course, you see in a situation in which the behavior is completely periodic, so in stationary conditions, it must be that VO and V in have opposite sign, because of course if Vin is positive and the current increases during T on, then the current must decrease during T off, and which means that VO must be negative. Okay? So the situation is the following here. If we plot IL as a function of time, again we have a typical plot that we always see in these converters. During T on, the current increases, and this is T on, which is equal to D times T. The derivative IL, DIL over dt is equal to V in over L. And during T off, of course, we need the current to decrease. Let's say that this is T off. The current must decrease, which means that DIL over dt is equal to VO over L, and therefore VO must be negative. Of course, we can, again, as we do, plot, calculate the total variation of the current in a period, and what we have is 0 is equal to the variation during T on, which is V in over L times dt, plus the variation during T off, which is VO over L, the derivative of the current as a towards time, times T off, which is 1 minus D times T. And therefore we have, you can simplify and remove T and L, and you can see that we have that VO over V in is equal to minus D over 1 minus D. Okay, this is clear. As you can see, we have a minus sign. Since D is between 0 and 1, the ratio is always positive, and therefore VO over V in is always negative, which of course is intuitive with reference to what we have said up to now. We always invert the sign of the voltage, and you can see that as, depending on the value of the duty cycle, we can have a current that is larger or smaller than V in a voltage, an output voltage which is larger or smaller than V in absolute values. For example, if D is equal to 1/2, you can see that the ratio is equal to -1, which means that the output voltage is exactly equal to the input voltage except for the sign. Okay? If D is smaller than 1/2, we can have an output voltage that is smaller than the input voltage. If D is larger than 1/2, the output voltage is larger than the input voltage in absolute module. Okay? Of course, the sign is always opposite, is always negative. Again, it's just a different combination of positioning the inductor, the capacitor, and the diode. Please consider that basically the diode is only an additional switch, basically in terms of behavior, and we always need this transfer of energy between the inductor, the capacitor, the input, and the output. Because remember that during T on, the input voltage provides energy to the inductor, and the capacitor provides energy to the load. During T off, the input is disconnected, and the inductor provides energy to the capacitor and to the load. So there is always this let's say, oscillating behavior of the energy in the inductor and in the capacitor. Ideally, if these devices are ideal, basically during one part of the cycle they absorb energy and they release all the energy during the other part of the period, but they never dissipate any of it. They do not dissipate energy, ideally. Okay, of course this is a particular condition that we have called continuous conduction, because again the current in the inductor is always larger than 0. Also in this case we can evaluate what happens at the boundary between continuous and discontinuous conduction and in discontinuous conduction. So again, during T off, the average current through the inductor goes at the output, and therefore if we reduce the current required by the output, by the load, we reduce also the average current in the inductor, and then we move down this curve. So at the limit between continuous and discontinuous conduction, we have that the current in the inductor touches 0, boundary between continuous so this is the boundary, this is T on, this is T off. So so the peak current is important for us because it gives us also the average current in the inductor. The peak current can be computed by considering the upper side. So for example, V in over L times dt, or minus VO over L times 1 minus d over t, considering this slope. This slope is VO over L, and the time is 1 minus d times t. So we can use this expression or the other expression. Probably this is more convenient because we already have a dependence on VO. Therefore, the current at the boundary, the current in the inductor at the boundary is half the peak current, and therefore is equal to VO over L over 2 1 minus d times t. Let's take it this way, okay? Let's assume instead of putting a minus, since VO is negative, I consider the absolute value of the output voltage, okay? Again, the current at the output is equal to the average current at the output is equal to the average current in the inductor times the fraction of time during which the current in the inductor goes to the output, and this fraction of time is 1 minus d, because only during T off the current in the inductor goes at the output. So what we have is something like this. If we substitute this expression, we have something like this. So again, we can do the usual plot of the current at the boundary, output current at the boundary between continuous and discontinuous conduction. Let me write it. Output current at the boundary continue, discontinuous. conduction. So what we have is, if we plot it as a function of d is something between 0 and 1, what you see is that when d is equal to 0, I of b is maximum, and then when d is equal to 1, I of b is equal to 0, and we have a sort of, we have not a sort, we have exactly a parabolic behavior, because we have 1 minus d to the power of 2. This maximum is the maximum value of I of b is I of b max, as you can see, is VO times t over 2L. So above this value here, for a given t above these values, we are in continuous conduction, and below we are in discontinuous conduction. These are the two quantities. Of course, what is important to recognize is that in continuous conduction, if you remember, the duty cycle only depends on the ratio of the output to the input voltage that we want. In discontinuous conduction, of course, we need to check, but I mean, remembering what we have seen in the other cases, of course you will see that we will have also a dependence of the duty cycle upon the output current. This is something that we can verify pretty rapidly. Let's consider the case of discontinuous conduction. So again, this is a concept that we have seen in different, let's say, shapes for all types of converters. During T on, the current in the inductor increases. We are charging the inductor. During T off, the current in the inductor decreases. The current passes also through the diode, so it cannot go below 0. If it tries to go below 0, the diode goes off, and the current therefore goes off, goes to 0. So we have two different times. We can call it delta 1t and delta 2t during T off. Delta 1t and delta 2t. Of course, I think it's useful to let's say, write explicitly what happens. In this case, the switch is on and the diode is off. During this condition, the switch is off, but the diode is on. During this situation, the switch is off and also the diode is off. So again, we can try to, let's say, evaluate the average current in the inductor and to connect it to the average current at the output and to relate it to D again. So let's do it in different conditions. So the delta of the current in the period is 0. So let me write in this way. E at time t minus E at time 0 must be equal to 0. This is time t and this is time 0. So this means that the variation during T on, which is V in over L times dt, plus the variation during the delta 1t, which is VO over L, that is this is the slope. V in over L is the slope during T on, and VO over L is the slope during T off, plus VO over L times delta 1 T plus 0 is equal to 0. Oops. And therefore we can solve, remove T, remove L, and we can have this expression, which is easy to recognize. VO over V in is equal to minus what? Minus D over delta 1. This is what we have in discontinuous conduction. And of course, we can repeat the same consideration that we have done before. The ratio of the output voltage to the input voltage, because the converter ideally does not dissipate anything, is also equal to the inverse of the ratio between the input current and the output current. So once we have it, we can compute the average current in the inductor, which is IL large is equal to the integral of the current in time in a period divided by the duration of the period, as we have written before. So the integral of IL in dt from 0 to t over t, and this integral is equal to the area of the triangle here, which is the base times the height. The height is let me write it as a function of VO. Probably we can do that. Well, we can write it as a function of V in. Okay, maybe it's easy. So V in over VL times dt. Okay, so this is the peak current divided by 2t. Again, t and t go away. And once we have that, we can know that the current in the inductor passes through the output only during the time delta 1. So basically we can write that the output current is equal to delta 1 over delta 1 plus D, because the current to the inductor, which is this one, here the inductor is detached from the load, only passes through the inductor during this period. So if we do the substitution, we have something like this. Let me write here delta 1 times T over 2 V in over L times D. So finally I can take delta 1 from here, and if I take it from here, I have something like, instead of delta 1, I can write d over VO times V in times T half V in over L times D. So to summarize everything, I can put d to the power of 2 times T over 2 LVO over V in. Now the only thing which is important for me now is that all these quantities are, this is V in square, all these quantities are constant, and therefore the relationship between D and IO is the following one. D is proportional to the output current to the square root. So again, while in continuous conduction D is independent of the output current, in discontinuous conduction D is proportional to the square root of the output current when all the other quantities are fixed. This is something that we can summarize graphically. So let me take again this expression. I want to take again this part that we have obtained this expression. Let me write D as a function of the current, and let me summarize this part. If I want to check the dependence of the duty cycle on the output current, I need to consider the following things. In continuous conduction, what we have is that VO over V in is equal to minus D over 1 minus D, which means that D is only dependent on VO over V in. At the boundary between continuous and discontinuous conduction is given by this expression that we have written before. This is EOB max, and this is 1, and this is a parabola. And therefore, in continuous conduction, D is independent of IO. So we have an horizontal line. For example, when D is equal to 1/2, let's assume this is 1/2, here we have VO is equal to minus V in. And all these other lines correspond to different values of VO. But again, the important thing is that these lines are horizontal, because they are D is independent of IO. In discontinuous conduction, except for the precise expression, the important thing is that D is proportional to the square root of IO. And also, the other thing that I need to consider is that of course, at the boundary between continuous and discontinuous conduction, the lines corresponding to the same VO or V in must be connected. So I will have something like this, star, ta. These are curves that have the shape of a square root, all pass through the origin, and of course are connected to the proper horizontal line at the boundary between continuous and discontinuous conduction. So this is continuous conduction, and this is discontinuous conduction. So this is more or less the same type of behavior that we have seen in the case of the boost converter. As you can see, the buck boost is very close to the boost converter in behavior. Again, if we have a rapid variation of the output current, we need a correspondingly rapid variation of the duty cycle if the voltages are kept fixed. If we move from here to here, of course, the duty cycle must vary a lot. Okay. To first order, the output voltage is constant. Okay. Now, in practice, what happens if we consider this converter? In practice, what happens is that we have a ripple on the output voltage, and you can see it clearly because you see, if you look at this plot, during T on, the load is only receives current only from the capacitor, and when the capacitor provides current, it is discharged. So it loses charge, which means it reduces the voltage. So if we look at what happens in detail, both the buck boost converter and the boost converter have the same type of ripple. During T off, the voltage on the load decreases because we have a capacitor which discharges. Okay, so we can have a look in detail by considering the buck boost converter. The reasoning is exactly identical for the boost converter. Ripple at the output. So during T off, we have this situation. We have a capacitor, the load, no, this is during T on, not during T off, when the diode is off, but during T on. During T on, the diode is off, right? And so this is the situation. So the diode is off, and therefore the capacitor provides current through the load. This is V, no, I took different sign. This is VO. So VO is negative, and the capacitor provides current to the load. So if I plot in detail the absolute value of VO as a function of time, actually it is not constant, it is an exponential, because when a capacitor discharges through a resistance, the voltage goes down exponentially. This is T on. Then we have an increase during T off, because the capacitance is recharged from the inductor, and then it starts again. So if we look in detail at what happens here, the output voltage is not exactly constant. Now consider that I have increased a lot the variation of the output voltage, just to show you the effect, but of course it's a minimum variation. But we can make the following reasoning. Basically, the initial part of the exponential is a linear curve, and so we can approximate it with a linear curve. What we can say is the following: basically, the voltage is varying only very little. This current is almost constant during T on. Let us call it EO, and this current corresponds to a charge provided by the capacitor, during T on is equal to the output current times T on. Okay? And of course, if the capacitor provides this charge, the variation of the voltage on the capacitor is equal to C, to Q over C, by definition of capacitance. If a capacitor loses a charge Q, the voltage variation is equal to Q over C. So this total variation, delta V, is equal to minus Q over C, which is minus IO over C times T on, which is also dt over C times IO. No, so we have an idea of the ripple that we can have, and of course it's pretty clear that in order to minimize the ripple, we can increase the switching frequency to decrease T and increase the capacitance. Okay? This is pretty clear. To reduce the ripple, the ripple is delta V, the maximum variation of the output is the ripple. The ripple delta V, we need to increase the switching frequency, which is the inverse of the period, and increase C. Sometimes this IO is given in terms of VO, can be written as VO over R, but it's much less important. If we write IO as VO over R, we have something like a ratio of 2 times T and RC times the duty cycle, which is always is between 0 and 1, times VO. So again, we need to make the time constant RC as large as possible with respect to the period of to the switching period. But I mean, it's the same as what we have written here. So typically, depending on the application, we have a maximum ripple that is allowed, and in order to match the maximum allowed ripple, we need to increase as much as possible the switching frequency and the capacitance of the converter. Okay, if you consider the situation, the same thing also occurs for the boost converter. If you look at the boost converter, we have said the same thing. In the boost converter, during T on, the diode is off, and we have that the load is only connected to the capacitor. So for the boost converter, we would need to repeat exactly the same type of reasoning. I lost something. Okay, so same considerations. For the boost and the buck boost converter. Exactly the same considerations. Okay.